All right, everyone, we are back to this very interesting Forth-like language. Um, yeah, so today I wanted to actually make this run in a virtual machine or something similar to that, so we can compile so we can compile it into machine code in a easier way, because currently it's like running in the syntax tree itself. Well, not really a syntax tree, but like, yeah, you understood the idea. And yeah, I have quite a few ideas for this project. Some of things have been popping into my head. One of them is to add types and all of that. I know that people in the past have add added types to Forth, but I wanted to do it in a slightly different way with like more modern features. But let's see how it goes. So today, I think it's all about cleaning all of this shit and turning it into a proper intermediate representation thingy. So yeah, so maybe here instead of this exec, um, we can comment this. Right, let me just move my microphone so it doesn't hit my arm. We can comment this and we can probably compile something. So here I can create a file. Yeah, I can call it out, and it's going to be fopen. Um, what can I can say out for now. Yeah, it's fine. And here I can say write, actually, write binary. All right. So then I can basically just start writing stuff into my file. Um, yes. So here, in that case, I can have a function, something like static. This actually shouldn't be inline. This code is all going to be sent to trash, so it's fine. And here I can just clone this. It's simpler, like so. And here I can um, I can call this like compile or something. Yeah, we can compile these words or translate rather. Yeah, this is more like a translate. So we are basically going to translate this word into some sort of intermediate representation, right? And here we also need to accept the output, right? So this is output. Where are we going to put this translation? And here, instead of executing stuff, we actually just need to write the following. So when we have words that is all digits, we can do this. We can do fprintf. We can output it into the stream, and here the instruction to push number can be, for example, lit, I guess. Yeah, it can be lit, and here we can do that, like so. And in this intermediate representation, I want each and individual line to be an instruction. So like assembly. So this is going to be very similar to assembly. So this one is going to push a literal. Then we have the plus, and the plus can also be quite simple. We can simply just say add, and that's it. We don't need anything else. Then for the minus, it's also the same thing. We can do sub. For this, we can do move or multiply. And here we can just say div, right? Like so. And all of these, this can also be, yeah, this can also be a like a primitive instruction. We can say loop. Drop can be like drop or something like I'm just following the 3-letter schema. This one we are not going to support for now. Yeah, this one we're not going to support for now. Swap we can support. You can say something like swap. This one we are also not going to support, so we can remove it. What else? So we now need to handle, yeah, we now need to handle the stuff. So we should have like a table with a vocabulary, with all of the words in the vocabulary. So let's say like def struct, and we can call this vocabulary, right? Or actually, well, let me think. It's going to be similar to the definition, right? But in this case, you're just going to have a pointer to the where the code of that word actually is, right? So let me think about it. Yeah, we can have something similar to that. So let's say word size, or yeah, word size, or word max size. Yeah, word maximum size, we can have like 64 characters. And here we're basically going to have a constant char pointer name, right? Actually, it's going to be like this. But in this case, instead of storing a body, we need to store like the label or something. How do I want to represent this? So let's say I have a file, and I have this. Let's say I have these definitions. So something like I don't know, to dupe, right? And to dupe is going to have like an A and a B, and it's going to output an A, a B, and a B. I don't even know if I have enough primitives to do this kind of stuff. So if I do a normal dupe, yeah, it's not going to work. Yeah, so let's say something similar, so like 2 plus, right? Which is basically this. So basically, this, and then I have other codes, like I have like 3 plus, for example, which says 3 and then plus, and then I have the actual code, which I push 2, and then I do 2 plus, and I do 3 plus, for example, right? So my intermediate representation will need to have these definitions plus that, right? So when it starts to be compiled, I need to read this, okay, it's intercompilation mode. Then this needs to generate a label, something like this, right? So in this case, I can say something like this. This is a label, right? And then I need to do that. So this is going to be lipt2, and then add, and then set, right, for return. And then we have this exits compilation mode, this enters compilation mode again. We need to do again label 3 plus, then 3, then actually lipt3, then add, then return, right? And then I need my entry point, right? So this is going to, I don't know if I'll need to, that's very interesting actually. That's very interesting. Because if I want to support colon like this operation during runtime, I'll need somehow to actually have it, like, right? It needs to be like convert it to some kind of instruction that in my intermediate representation I'm going to have. That's very interesting. But let's keep going. So this then is with 4, and then here I'm gonna need like a call. Like, I don't know if I'm going to keep. Yeah, maybe I'm just going to keep the instructions like this, so it's more explicit. So then I need to call, and I need to call a label, right? Yeah. So I can call a label. This is going to push stuff into the return stack. Right, this is going to push stuff into the return stack, and the ret is going to read stuff from the return stack. So that's one way of doing it. That's one way of doing it. It's pretty cool. That's what I want. Then this does that, and that's it, right? So this is one possibility. Another possibility is to have like a dot vocabulary at the end, right? And here I can say that 2 plus is defined on the line 9. So I have the label, and then the line where that code starts. Then I can have like something like 3 plus, and 3 plus it is defined on the line 13. That's one possibility. And here at the top, I can always start with something like this: call __ start, right? And at the bottom, once I actually know where my first like instruction starts, I can just say that. Here I know that my first instruction is actually on the line 17, and I can say 17. That's one possibility. And in that case, I would not need this. I will not need this. And this will actually change. So this would be still be 9. This would be line 12, and this would be line 15, right? And I could have something like this. So I could have like a code section, right? I could have a code section, and then the rest, and then a vocabulary section. But then how am I going to execute this colon definition? So if I happen, well, I could have it. So I could literally say, okay, my colon definition, yeah. But then it would need, okay, let's go simple with simple stuff for now. So I'm not going to support macros just yet. I want to actually like have an idea of how this is going to work in a simpler fashion. So I don't know which one of the approaches is the best, to be honest. Having the lines or the labels, because if between my intermediate representation and my actual machine code, I do some kind of optimization, it may make, yeah. Let's keep it like this for now. So let's try it like this. So here I would basically just have a constant, and this can be like a size t line, right? So in my intermediate representation file, this is going to point exact location, the exact line of the instruction, of the first instruction of this word, right? The definition of the word. Cool. So if I find that's that, so then I basically only need to say else. I basically just need to find, and in this case Yeah, we do it by name. Okay, so we can basically just say call, and then I can just say swap. Okay, it's easier. Call, and I want you to call these specific words, right? So we can use the word by name, but it's also probably important to confirm that the word actually exists in the vocabulary, right? So this is actually a word, right? And my vocabulary is going to be an array of words. And I can define so this is very similar. Yeah, 2048 should be enough. So this is very similar to what we had previously, basically. Here, before actually appending the, well, it doesn't, well, yeah, I guess, before, yeah, it can be here. I can basically just reverse this, and here I just need a static size the vocabulary count, right? Something like this. I just do that, and here I just need to find and make sure it exists. I'm not going to use it for anything. I just want to make sure that it does in fact exist. Something like this. I could just clone this code. Yeah, it's easier. So say vocabulary, and this is can be a find. Vocabulary find. We can find the words, right? Yeah, we can. Well, yeah, it's more like a name. Here we just need to traverse that, and then vocabulary I dot name. Okay, so if I do not find is less than 0, then we just need to report an error. Try to use an undefined word, something like this, and we can exit actually with exit failure. So this is actually going to fail the entire thing. Okay. And this is just a check. We wouldn't need this to execute the program. This is just a check to make sure that everything is okay. Cool. So we now need to support the different modes, right? So let's go to this exec, this very cumbersome exec. We can keep this compilation mode, sure. But here we can copy this. If the current word is a colon, sure, we increase the compilation mode. This could be, let's turn this into a boolean again. Is defining, or actually definition mode. Let's call it definition mode. Right. So let's simplify all of these. If it enters that, we just do definition mode equals true. Then we return because we don't need anything else. Else if we find that, we need to do a few things. So first we need to set the definition mode to false, right? Then we need to print red for the return, right? So we can do something like this, and we can say red. What else do we need? I think that's everything actually. I think that's everything. And then we can exit the function. Right. So yeah, and this is very interesting because when we are not like interpreting the code, we are just like compiling it into intermediate representation. We don't need this stuff, right? Because we are only going to execute afterwards. So we don't actually need that, which is very interesting. Right. So here, when we enter definition mode, oh yeah, we need one thing. We need one thing. We need to get the thingy, the name. So what can we do for that? All right, that's interesting. So we do need to do the following. Here we need to store the line counts. So let's say this is a size t line counts. It's going to be 0 at the beginning. Yeah, this may be a bit stupid. Like this line stuff may actually not be that great. I think I'm going to bring back the labels. So yeah, well, but it would be so nice to have, but this can be like an internal representation. Yeah, so instead of having like a separate vocabulary, we would just have this. But here I can say label. Okay, it's fine. Here I'm going to say label 3 plus, and here I'm going to say label 2 plus, right? But in this case, once this starts executing, it enters here. Oh, yeah, so this will first need to scan all of the instructions, the intermediate representation, collect all of the labels, construct its own vocabulary, right? Yeah, construct its own vocabulary, and only then start execution where it should. Yeah, on the very beginning. I mean, it's fine, I guess. And it's probably more useful when we are compiling like here. So in that case, our vocabulary literally only needs to be an array of strings, right? Because I don't think we will have anything else. So we can even make it simpler. You can call this the actual vocabulary. What was, I always forget what I think. Yeah, I actually think that's how we do it. So this one can come here. Vocabulary max size, and here I can move probably the count to the inside, something like this. And I can zero initialize it, right? And here I just need to say, here I can just call it words. I can say vocabulary counts and vocabulary dot words, and I just do that. All right, that's nice. So when I enter definition modes, I do this. I just enter the definition mode. I then need to collect something. So if I am inside the definition mode, I basically need to collect the current words and turn it into a label. So I just do this, that, I say label these words, right? I just say that, and I can instantly return. I don't need to do anything else. I don't need also this anymore. And to be honest, I could literally just flip this instantly, right? I could flip this instantly, and then here I would not need to do anything else. And I could just simplify all of this and just make this be a chain of else ifs, so I don't need these returns. Yeah, don't need this extra returns else if, and so I have this much simpler implementation. Okay, it does look good. It does look good. So this is basically going to translate my fourth like language into intermediate representation. So this was also not going to do anything. Right. That's very interesting. Okay. So I think that's the entire, actually, I think that's the entire implementation. So if I now do the following, translate these words into whatever the output file is. I'm gonna call it output. Here I don't need this, or actually I could use that. I could use that actually. So just to test it, let's see how it goes. So if I do the following, I define a function, let's say 2 plus, which does 2 plus, and then returns. This does not have anything. Why doesn't it have anything? Oh, it only, okay. It only adds it when I exit the program. Oh yeah, okay. Okay, let me clean this up. Then let's try again. 2 plus, then that's, okay, that's fine. So I actually need to define it. 2 plus that. Okay, and then I shift and save. Okay, didn't save anything. I need to flush the file probably, right? Or actually, I just need to quit properly. Okay, I do quit. Okay, so basically this created a label called 2 plus. Then we have the code for 2 plus, and then that's it. I mean, I guess this should be okay. So if I add other definitions, I don't know, like swap loop, which literally just does a swap followed by a loop, and then I add, I don't know, square, which literally just does loop multiply, and then I quit. This is going to add like the labels properly. Okay, okay. And what's actually going to happen? So if can I copy this? Yes, I can. If I do that, and then that, and then I do something like 2 square, oh, that's interesting. Oh yeah, because I'm never pushing the word. Yeah, so it basically, yeah, it calls square. So when it basically, so here the only thing missing is like a call to start, right? And then here I need to add a label like that, right? Okay, so let's try to handle that. I can say something like as start. I think that's pretty explicit. We begin at false. And then I probably need to move this lower, I think, because here, if I do something like if, well, yeah, if it's not in the definition mode and it doesn't have a start, then I need to add the label under start, or the the label start. So let's try that. If it's not in definition mode and it doesn't have a start, I first need to set start to true. Okay, so it already has a starting point, and I need to add the label let's call it start or something. Right. I basically need to do this. And if that's the case, I first need to check for this. Yeah, I first need to check for this. Like so. We first check this. So we first check if we are entering the definition mode. Then we can do everything else. Right? Because that's not needed. And in this case, if for now I'm not going to support macros, by the way, so since I'm not going to support macros, I can just report an error saying, okay, so if we are in the definition mode and you're trying to define something in the definition mode that is already like active, try to define a word within a definition and open or an existing definition. I can just say definition here. It should be okay. Yeah, try to define a word within definition. So this is going to prevent us from like doing macros, but that's fine. Then this is going to set that is going to like continue. Then the next thing is going to check exactly. So this should work. Let's try to use it. So if I do something like swap dupe, which is like a swap and a dupe and a return, that's cool. Then I do 2 3 swap dupe. I'm still missing this thing, but that's fine. Here, what did it create? Oh, that's not what I want. Oh yeah, because yeah. So I can only reset. I can only reset this when I get into the return. So that's another thing I need to do. Let's try again. So swap dupe like this. Then 2 3 swap dupe. Okay. It didn't complain for some reason. That's strange. Swap dupe. Okay, let's just see what it generated. Why did it add one last label here? Oh, it's always adding labels. What? Oh yeah. Yeah, it makes sense. So that's why it didn't complain. I can add another flag saying as name, right? So when I enter this, I need to set as name to false. I can assume this is true at the beginning. And here, I only need to generate a label if we are inside the definition name and we do not have a name currently for the current definition. Like this. So as name, then can turn into true. And we only reset this when we enter a new definition, and that's it. Everything is fine. Cool. So let's try again. Loop and then finish. Okay, so 2, 3, swap, loop. We are going to have a complaint, that's fine. But here we have a label. Yeah, that's okay. So we have a label, swap loop return, and then we have the label for start with a literal 3 and a call to swap loop. So at the end, actually at the beginning, we only need to do the following. Fprintf to the outputs. We literally need to do call __ start. And so we call the start, and this is basically going to call this and execute this. This is going to jump to there, execute this, return, and go back and terminate the program. Exactly. So I could, let me try to do this one. So I could pipe the following data into it, so it's easier to test. Swap loop, swap loop, return, then 2, 3, swap loop. If I do that, isn't that how you pipe stuff? Is it double thingy? And then I do quit. Man, how do you even do it? Well, I could do the other way around, right? I could say echo and then pipe it into the fourth. Is this going to work? Okay, it's going to work. Okay. So yeah, it's basically so the intermediate representation is super simple, and it's working, right? And it's working. So now we are only missing this stuff. We only need to add stuff into the vocabulary. So let's do it, right? It's very simple. We can do this just to copy it and be simpler. Vocabulary dot add, and we can actually call this a word now because we only have like words inside of it. Here we just need to say vocabulary dot count is greater or equal than vocabulary max size. Try to add a word to a full vocabulary, right? Then I check if my word is greater or equal than the word max size. Till maximum word size with that, sure. Here, here, and here. And we can fail, it's fine. And here we just need to say, okay, vocabulary dot words at vocabulary dot count exactly is going to receive this word, right? And we can actually increment it right away. So we have this single instruction. Cool. So now, after we do that, here, oh fuck. Well, actually, we are fine, because here we just need to, once we added label, we also need to add this to the vocabulary. So the vocabulary already knows about it. Yeah. Yeah, basically. All right, so if I do that, then oh, this discards const qualifier. Okay, so let's not have it a const, I guess. To try to define a word within a definition. Why did that happen? So let me not do all of this for now. So if I say 2 plus that, okay, 2 and then 2 plus. Well, it's working, I guess. And then I don't know why it complained. We can debug it later if it's actually a bug. So this is called start, call there, then literal 2. Is this correct? What did I do previously? I did 2 plus, and this only added 1 literal. So there's something strange. There is something strange. Where did the other 2 go? So this one is correct, right? So this one is correct. That's very strange. So, oh yeah, of course, because this needs to be outside. Yeah, of course so. This needs to be outside, like at the very top, because even though we add a label, we still need to parse the word, like we still need to compile it, right? So let's try this again. It still complained for some reason. Try to define a word within a definition. I'll check it later. So here, let me don't save this. Let me try the other one, the simpler one. So define 2 plus as 2 plus that, and if I do 2 plus, and I quit, this now as a call to start, as a label start, let's add hat. Okay, now it's adding it properly. And why did it complain in the other one? Let me check. So it was, so I did swap dupe that. So if I do it like line by line, does it still complain? No. Okay, so I think the issue is when I do a definition of something and I add stuff like after it. No, it's still fine. So I really don't know, like this echo stuff is a bit strange. Okay, but it's working. So I don't actually need this file anymore. And this intermediate representation. Oh wait, no, this is broken again. Oh yeah, fuck. So I need to first do this shit, right? Then I need to do that, and this needs to fall through. And here, so I basically need to do early return. I think this is actually correct now. So swap dupe, then I do, I don't know, 2 plus, and then I would do like a few things here, like swap dupe, and then 2 plus. If I run all of that, it didn't complain about anything. And then in output, I have a call to start, I have swap dupe defined, I have 2 plus defined, then my start begins, and let me just double check everything is okay. So I have literal 2, literal 3, lit 45, a call to swap dupe, and a call to 2 plus. That's fine. Okay, so now it's actually working. Cool. So yeah, so this is basically my translate, and this is translate. I think I'm just going to create a separate C program just to keep things simple for now. We can then bundle everything into a single executable. But let's call this one, I don't know, P4C or something. So we can call it, yeah, P4C, and this is basically just going to compile shit. Okay, it's working. We can quit. Um, yeah, we can actually remove that. And then we can have like a p4th like main executable, which is just going to execute the bytecode, right? So let's do the following. It's basically again the same. Something like this, return 0. Here, let me check. Man, if I do man m map, I know this is only for Linux, but do I want to use mmap? I actually don't need to. I actually can keep using standard IO, because since every instruction is like in a singular line, I can just read the lines and everything is fine. So yeah, I can just use standard IO. Then I can do file. So this is my intermediate representation. Okay, it's source of codes. I can click code, F open, and I can literally just slap output right here, and it's going to be read like so. So now we need a very similar loop to what we have here, right? Yep, we need a very similar loop. Let's literally just copy it. We don't need this. Here my buffer, let's define it. I think it's buffer size. I don't know. We can 1048 or something. Like so. Can have buffer size, and here is going to actually read from the file. We can call it file. It's actually going to read from the file. Why are you? Oh, okay. So it's going to read the line by line from the file. Here we don't actually need these, and I need to fgets. I need to go back to fgets because I need to know when end of file is reached. Sure, but where? Okay, so I can basically check for null. So if not that, I can break. That's basically it, right? Right. Then I can literally just break this by space, because I know that this is only going to have a single space in here. This is going to be my op, or my instruction, right? Call it inst. Right, so this is going to be my instruction, and here here I can do the following. So if I basically need to copy all of this, right? Yeah, I just need to copy this. So if my instruction is equal to what instructions we support, already forgot, like lit, for example, which is a very simple instruction. So if my instruction is equal to lit, let me just remove all of this. We basically need to append that into some kind of like memory. So here, let's define our VM. Basically, we are defining the internals of this virtual machine for now, because I'm going to execute it inside the virtual machine in this episode. So we can just say that def struct. Well, it doesn't even need to be like that. Let's say static VM, and this is basically my code section, right? So I can define a new num something like this with inst, and here I'm gonna have basically inst lit and then all of the other instructions that I'm gonna add later. And here I'm gonna have the instruction segment. Do I want to have this separate? Do I want to have this separate? To have separate codes and instruction set? Probably yes. I guess. Does it make sense for the program to write into its own? I rarely use that, to be honest. And we can have like a well, if we add quotes, we would need that actually. We would need in that case, let's have something like, well, in that case it's hard because yeah, we can have a cell. Yeah, it's basically like a memory cell. It needs to be a union, right? And inside here we can have like an instruction or other things, right? We can have an instruction, we can have numbers. So we can say like int64, and this is like an i64, I guess. And then we are going to have a memory with a bunch of cells in it. So memory size, let's say 2048 for now. I don't want to worry about allocations right now. And here we are just going to write stuff into the memory, right? So we need like a pointer or something like indicates the memory, and this is not during execution. We are just going to need this pointer while parsing the or consuming the bytecode file or the intermediate representation file. So let's call it mp or something, right? And then we just say something like vm.mem vm. Actually mp plus plus, and here dot instruction is equal to instruction literal, right? And when we have that, we already know that we should have at least one more word, one extra word in there. So we just need to say this, and this should be the digits, right? Yeah, exactly. So these are the digits. Let me do the following. I want let me create an helper function like voice vm scope push or add cell, and this basically needs to consume a cell because I want to like guard this. I don't want to have like memory and safety issues in this specific segment, because it's very likely that I'm going to surpass this memory size. So I want to be worried, like I want to be warned about it when it happens. So let's just do this. It's fine. So I basically did that, but before it I just check if the current MP is greater or equal to memory size. Then I need to do some error, right? Throw some error. Try to add a cell to full memory or something. Let's also include standard lib. Cool. Just so this way I have like more stability. I don't know what the fuck is going on. So here we would need to basically push this, and this is going to be an instruction. This is inst lit, and that's it. So something like this. Then we have the digits. Do I need like a specific function for it, or can I just inline? I think I can just inline it, to be honest. It's like it's so simple that I can literally just do this. And in this result we are basically just going to have the i64 or the cell, and we can zero initialize it, and here we can accumulate directly into the i64, and then we just need to add it like so. And I can call this like something just to be even more explicit. Alright, so here we can also extract this into a separate thing, just like to be prettier. We didn't add to it. So this is the instruction, and we push the instruction. So we push the instruction, then we have the digits here. We can also have a guard for this if we want to be fancy. So if digits does not exist, so if there is something very broken about our compiler, here we can say error, actually error, try to add, I can just say memory is full. Something like this, because this is like a developer error, so it's fine. And here we just want to say error expected digits in lit, after actually lit instruction, right? So that's a literal instruction which holds an argument. Then what else do I want to add? Well, I guess I can add everything, right? So I can come here, the add sub mul div instruction. They should be pretty simple, so I can just do both that, sub mul div, god I cannot type, div, what else, dup, drop, and swap. They're also pretty easy. Drop, and swap, like so. Then I need the hardest one, right? Well, I also need to write. Write is also pretty easy. Right? But then I need to handle labels and I need to handle calls. So let's maybe handle labels for now. Do I need to have labels inside my VM? I don't think I need them. I don't think I need them. So instead, I need to like create my own vocabulary, as I was talking about previously. right? So I need to more or less copy this. Like in this is like the only like parsing stuff. So this is parsing, not execution. This is I'm only constructing, like grabbing the program from the file and putting it inside the virtual machine. So here I would need a similar size, a similar thing. But here I would need to say something like this. So struct, and this can, yeah, this can be my words. But here I would need to have like the shard words, which would have this stuff. And here I would need to have like an address pointing at the memory, right? So this address would point at the start of this stuff, right? So yeah, so when I encounter, oh, and everything else is pretty trivial, I guess. Everything else is literally just because none of these has arguments, so I can just do this, add a bunch of else ifs, copy this stuff. Actually, yeah, let me be even smarter. I can say that else if this, can I still, yeah, I can still copy it, get this and put it there, boom, boom, then damn, okay, so that's should be fine. And here, oh, it has an extra one. Well, I can actually remove them like so, like so, and then I can add an X invitation, and here it's fine. So here is not actually inst, it should be just the name, like so. And here, well, let me just inline this, I guess. It's just easier. So I can copy and paste just a smaller amount of code. Like that, right? I just need to grab these names, like so, move code there, and boom. Okay, so we now support all of these instructions. Let's add support for label. Now label is going to be a little bit different. So label. For label, we are not going to add anything into the memory. It begins right away like that. We will instantly try to parse the name, like whatever name we need after label, right? And then we need to do something to it. So we basically need to go into the vocabulary, and we can have a function. Like the add, like so. Well, I can say, yeah, can be words. Can labels be anything but words? Possibly, I'd say. So this, we can call this a words. Yeah, let's keep it name. String or yeah, let's say name. So this needs a words, and this is fine. This is fine. So we are going to copy it into the vocabulary, but we will need to do a few things as well. So in the words themselves, when we add this, the address of this word is going to be this thing, or actually this thing plus one, right? that sync plus one, because the current address, or actually no, it's actually this one, because whenever we add a cell we instantly increment it, so it's fine. So yeah, that's basically it. So we add a word that points at a specific address in the virtual machine memory. Cool. So here we just need to say vocabulary underscore adds, and we add that stuff. I can call it a word because let's say it's a word. Cool. And that's basically everything we need for the label. And then for call, we can do something similar to this, because call is also going to need a literal, right? So call is basically, oh no, call, because call needs to push stuff into the return stack. Yeah, so we cannot have jump instead of call. Okay, it makes sense. So let's copy this, all of it, and here when we find call, we push a call instruction which we need to create. It can be like this, so call and return. And here we expect some, we can actually call it label. Why not call it label? Yeah, I guess. Here we expect some labels, actually a single label, expected label after call, and then we need to find the label in the vocabulary, right? Something like this. And here I can just say, yeah, I can replace this by label. So let's call it the things as they are. And yeah, I can call it value, label. Here we have labels, labels, counts. Here I'm going to find a singular label. Here I need to replace it by label, right? And then labels, label. Okay, so once we find, yeah, so basically once you find that, so here we just need to say vocabulary find, and we need to find this label. Also, let me replace that. So we need to find the label. Once we find it, we will get the index, right? The index in the vocabulary. If we can add a check, if index is less than 0, we can also put not find, or actually undefined label. Oh, but that's, yeah, because we'll need to basically do a two-pass compiler, right? Because if I do call start at the beginning, I'm not going to know where the start label is. Yeah. So, and yeah, this needs to report an error, but we can only treat the calls, the call instructions, when we have gone through the entire file at least once, which is a very interesting thing. So undefined label in call, and here I can just provide the label, and then this is going to be my address, right? And my address is basically going to be here. I can add it. It's simple. I can say size t address. And here my address can have the whatever is inside vocabulary dot labels at this particular index dot address, something like this. And then I can just add my address cell after that. But so here we need to do a first pass, right? And we need to ignore all of the calls, right? Yeah, we basically need to ignore all of the calls, and only then we do a second pass where we fill in whatever was missing. So this is the first pass, right? And then we have a second pass. Like this. Yeah, and that's why maybe the idea of the lines was not that bad, because we could instantly, and we would not need like two passes, but I guess this way is also okay. So I just need to copy this right here. I also need to copy all of that like so, and here I need to reset. So seek, I need to reset my file. So this is going to be file, I think I call it file, yeah, I called it file 0 and seek set. So this is going to reset the pointer. Like I can show you f6 this basically that sets the file position indicator for the stream, blah blah blah. So when we do seek set with 0 offset, it basically rewinds the entire file to the beginning. So we can do that, and we can read the file. I'm not trying to do this super optimal way. I'm just trying to have like a system that works. Yeah, and here we fit that. We can ignore, just ignore it. See, I call it this. See second pass, and everything else. I can say that we have an error, saying that unexpected instruction, right? And we can just provide the instruction like this. So after all of these codes, we should have a VM with some stuff in its memory, right? So I can just print everything that is inside of the memory. So this is just for like, this is temporary, this is not final code. And I can I can say the following. God, this is taking very long time. 1 hour, 13 minutes. I can just print the numbers, right? I can just print the numbers as they are. So with new lines, vm.mem I, and I can just custom to long int, and it's fine. This is just meant to be I can take that in that case. Oh, I see. Dot this. Okay, it's no longer complaining, so I don't even need to cast it. Alright, so let's first generate a very simple program. So my program is going to define 2 plus 2 plus that. So we have one single function. Then my program is going to have like 3, 4, 2 plus, and that's it. It's going to terminate. Let me quit. So now this should be inside of here. So yeah, we have the call to here. We have label to plus, lead to, add, ret, then 3, 4 call, and then add. Okay. So after this, we can also compile our bytecode interpreter, which, oh yeah, I forgot. There's lots of stuff missing. Okay, so I need to include string.age. What else? Incompatible type for argument 2, which is very much correct. I need the value here. What else? Here is probably something similar. Yeah, of course, I need the value here. What else? Oh, I forgot to, okay, I need to say this is a char. Implicit declaration. Yeah, I don't want it. I actually don't want it. Expected instruction. Oh, unexpected instruction. Unexpected instruction. But why is it saying that add is an unexpected instruction? Oh, because this is going to contain fuck. Okay. So, oh, I see what we can do. We can just add the space and that. Yeah. Everywhere. So everywhere we have str talk. Instead of just having the space, we can have that as well. Yeah. Because this is also going to like remove it from the final string. Undefined label underscore start in call. But we did define underscore start. We did define it. Yeah. So let's do the following. Oh, this is not what we want. Yeah, this is what I want. That's very interesting. So when do I, in label, I strip that and I do vocabulary add. And when I add it, oh, yeah, I forgot. Yeah, it makes sense. I forgot to put this. Okay. Okay. So let's try to see if this actually is something. So we have 0. Okay, so it read this, it ignored. Well, oh yeah, fuck. So I need to actually, yeah, I need to be smarter. I need to be smarter. So I need to have like an array of deferred instructions. I cannot like do this kind of blind second pass. I actually need to stuff here because I need to reserve space for my call instruction, right? Yeah. So I need to have an array of deferred things. It's actually going to be very similar to this. I'm gonna say. Let's just add it then. So this is the deferred. Is that how you type deferred? Let me check it. God, what's happening? Okay, deferred needs 2 args. Okay. So 2 args. And here, yeah, we are going to defer a label. Here is going to be a memory pointer, right? So we are going to basically defer a label in a specific location, a specific memory cell. We are going to have deferred max size, and here, yeah, deferred stuff. Yeah, so we are just going to fill in the stuff that we actually want. So here we can have something very similar. Deferred underscore adds. Here is deferred. 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 That's not how you type it. Deferred table. This is basically a table. This is the same stuff. This is maximum label side. I forgot to update this. And here, just do that. Deferred, 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 and this is not that. This is actually the current memory pointer, right? Yeah. So when we do this here, we don't ignore it. Actually, we have to do the following. We have to first push a call instruction like this. Then we need to push a zeroed out address. And this is going to be like the second pass stuff, right? And actually, yeah, we need to, since this add already increments it, the memory point is going to be pointing at this address. So we need to add it before we add the memory cell. And here we need to add the label. So all of this stuff needs to actually come here and there, right? And here I need to add the label. And we don't check if the label exists yet, right? We only check that afterwards in the second pass. So we defer this label and we just mock, like we just have a null address there. And here in the second pass, instead of doing something stupid like this, we don't need to do something stupid. Here I can actually do fclose because we are not going to need the file anymore. Here we just need to loop through all of the deferred labels. Defer.count I++, and here you don't need to do any of that exactly. None of this. I just need to get the label from deferred.labels I, right? Dot value, sorry. So this is going to find the index, and here we can check if the label actually exists. I can say this is called char label. I can extract it so I can report in the error, right? Then if it exists, I can basically just patch my vm.memory.cell. This is actually, am I doing this correctly? Yeah, I need to patch it in this specific location, memory pointer. So in this specific memory pointer, I need to set it to be equal to vocabulary dot labels dot actually index dot address. So I'm going to like patch it afterwards, yeah. And this is address. Right? So I'm basically replacing the 0 by whatever was inside the vocabulary at the end of the execution, right? But this is going to be fucked up because this now does not support threaded code, or no, it does because this is intermediate representation. So while we are compiling it, the labels of, like, we can overwrite a definition. Oh fuck, we can overwrite a definition. That's something I didn't think about. Yeah. So I can have labels, like multiple labels with the same name, and my code needs to proactively like call them. Well, I think I can think about that later. Let's just see how this works. All right, so we have 8 0 1 2 3 4 5 6 7 8. Okay, this is a call, it's correct. So here we have an 8, and then we have a 6, so it's going to call instruction at position number 6, right? And this is basically 1 and 2. 1 and 2. Then we have a label which does not append any instructions. Then we have literal 2. Literal 2, yeah, is a 0, so this is the position 3, and this is basically a 0. And then we need to get like the literal, which is, yeah, which is a 2, which is in position number 4, also correct. Then let me just move this. Then we have an add, and the add should be a 1 exactly. So this is a 1, and it is up at position number 5. And then ret should be a 9, yeah, a 9 because call is an 8. So this is a position number 6, and this is a 9. Then we have another label which does not add anything. Another lit which is 7 and 8. So 0 and 3, it makes total sense, that's correct. 0 and 3. Then we have 0 and 4, also correct. So this is 9 and 10. This is 0 and a 4. Then we have 8, 2. So 8 is a call, which is also correct. So it's 11 and 12. And this is a 8 and a 2. So this is going to call the position number 2. Is it correct? Oh, this is, fuck, this is 0, 1, and this is 2, 3, yeah. 4, 5, 6, 7, 8, 9, 10, and 11. And then at the end we have a 12. At position number 12 we have an add, which is basically 1. So this is basically what we add at the end in our memory. So let me just format this a little bit better. So basically this is the representation of everything. Cool. I think everything is correct, right? I think everything is correct. So now the only thing missing is to execute it, right? I think that's I can call it consuming. So this is a consumption part, and then we can have execution part. To execute this is actually going to be pretty easy, right? Because we literally just need to execute. Right? We can have like oh, but when do I know that this has altered? That's actually a very interesting point. So my program needs to exit at some point. I'll think about that. I'll think about that while doing this shit. So this is basically the execution. And now to execute our program, it's super easy, right? So we just do that. Here we need to think about this. So I'm going to tag this like so. And then here we literally just need to traverse, or actually switch the vm.mem I, right? And we assume we have an instruction. So we assume we always begin with an instruction on like address 0. And here we just need to do all of this. Right, so something like that. And now his execution is much faster because he's using a switch statement instead of string comparisons, right? So, and nonetheless, like this is still quite slow, because if we did this in machine code, it would be even faster. But everything at its own time. So you can break. All right, so if we have a literal, we need to basically, yeah, sure. We need to basically increment it once again. We need to read its contents as an i64, and we need to push it into the data stack. So our VM needs to have other things. Do I want to have my data stack in the same memory position as actually same memory array as the, I guess so. We can have everything in the same place, sure. So here I just need a data stack pointer, and I need a return stack pointer, right? So here, let me increase this. So this is basically 1 kilobyte, and here, let's have it like 4 kilobytes of memory. So here, yeah, where do I want this to grow? So if I'm placing, basically I'm placing the codes here. So this is my code inside my memory. Then I want to have a bunch of stuff in there, right? Unoccupied stuff. I need two stacks. I need the memory, the data stack, and the return stack. I can split these. How can I split this? So I can split this in half or something, and have like the return stack, or I can split this into thirds. Right, 1 kilobyte for something, I don't know, something like this, half and then half again. So I can have a bunch of codes and then some data stack and some, well, that's not a bad idea. That's not a bad idea. So I can have like data offset. So bstack offset. And my offset is basically going to start at memory size divided by 2, something like this. And then my return stack offset is basically going to start at that yeah, so that divided by 4. Yeah, that's basically it. So plus this divided by 4. So we basically have half of the memory for code stuff, right? And then we have the other half split in both in halves, one for the data stack and one for return stack. It's fine. So yeah, we can tune that later. And so here I only need to push stuff into the data stack, basically. So I only need to do that. And here I basically need to check if this is greater or equal than the stack offset, because we don't want to disturb the data stack. So we can copy these functions from here that we used. Yeah, for data push. Yeah, and say dstack push. And here we just have the vm.dsp, and we say, so the limit is going to be the return stack, the limit. And yeah, so vm dot memory at vm dot data stack pointer dot i64 is going to be equal to that. Yeah, then we can just use it. So we literally You just need to do that, and here we can actually pre-increment it, and we have everything. So this is the entire implementation of the literal instruction, right? Then we need the add instruction, and in this case we can do something similar. So here we can have the stack pop, and here we can only pop if it is greater than if it is less or equal than the stack of set, right? Try to pop an empty data stack, and here we can return this more or less. We just need to swap that by this minus minus. Okay, so here we can pop this and save it into a variable. What did I do? Okay, in 64 yeah, like this, like so. And here, since I want to be like slightly more efficient, I can just say, oh, I forgot a semicolon here. That's I can just add it directly into the VM without using functions. So I can literally just say vm.memory vm dot the current data stack pointer, right? I think so, because we popped the first one, yeah, and I just need to add it like so as an int64. I think this is correct. Then for sub, mul, and everything is going to be super easy. It's going to be the same. So that minus equals that, I think it's correct. Here going to be times equals. Here is going to be divide equals. Then for dup, I could just use this function as well. This stack top, I can do the same thing. And here I do that. So the top of the stack is -1. So I don't know if this is actually correct code here. I don't know if I need to subtract 1 or not. Let me think about it. So if I pop it, so if I have A, B, I pop this, so my stack pointer is currently pointing at here, right? I pop it, it points at here, and I have B on my thing. Then yeah, it needs to be negative -1. Exactly. So I guess it's easier just to yeah, I guess so. We can have it, we can extract both A and B, and then we can push like we did here, B plus A, I guess. Stack push B plus A, because I want to have proper errors and everything, so I don't mind having an extra function call here. So that's 70 sub multiply and divide, and then here for dup we just do this, and then this stack top, right? And you can break. For drop we just do that. For swap we can literally just copy this like so. Where am I? Yeah, I'm here. Break, and this is b stack pop, and this is b stack push a b, and then we push a, and then we push b. Exactly. Then for call, the call is very interesting. For call, we need to get the value afterwards, after the instruction, right? And we need to get it as an address, right? And we basically need to change. So this is currently the program counter. So this is not I, this is like program counter. So let's say size t program counter is equal to 0 at the beginning. Here, let's remove all of that. Program counter, right here, and I can say that my program counter now is that address. So I just jumped into there, and I need to do something else. I need to push my current program counter, or program counter plus 1, into the return stack. Do I have a return? Yes, I do. So I can basically add these two functions, and instead of this stack, I can do r stack like so, and this is going to be a size t, an address, right? Push into a full return stack, and this is not ESP, this is RSP, and we are pushing the address, and then we pop it. We need to pop the address, and this one is going to be that one, right? Yeah, so I have to pop an empty return stack, and this is RSP, right? So when we call a function, we need to do the following. So we need to do program counter plus 2, because the current program counter is the call instruction, the program counter after that is the address, and the program counter after that is the place where we need to go after when we return from the function, right? And that's it. And then in the return, we just do r stack pop, and here we just set the program counter to that. There is nothing else we need to do. Yeah, there is literally nothing else you need to do. So this should be more or less it. So now I still do not know how should I handle like program termination. I could have like an alt instruction or something, right? I could have an alt instruction that basically just or I could have an entry point, because if I define stuff after this, yeah, I should have all of the definitions bundled into a single place, and only then have my code. For now I can manually patch it. So let's assume we have like an instruction for alting. I say alt, and this instruction for alting is going to be like the rest of the instructions. So something like this, and it's literally just going to say alt. And here, if we have an instruction alt, we just break from the execution loop and we terminate, right? Yeah, I think that's fine. So if I execute my compiler and I say something very simple, so 2 plus 2 plus then this, and then I do my code, which is like 2 plus, like so, and then I quit, this should flush it into here. Don't save. Didn't it save? Okay, it saved it. So yeah, we have call start. It's going to jump to here. Here is going to jump to there. It's going to return. It's going to come back here. We can have the alt instruction here. We can manually add it. I'm going to think about this, how to do this in the future, but we can manually add it here. And at the end, just to test, we can just dump the entire data stack once the program terminated. So this is just debugging. I is less than vm dot data stack. Yeah, data stack pointer, because we only want to dump stuff until the data stack pointer levels plus. And I can literally just say something like this, and we can assume everything is an integer. So vm dot mem vm dot data stack pointer, actually I dot i64, and we can add a space here. We can add a new line at the end. So if I execute this, oh, I have a bunch of errors. Okay. Yeah, okay, redefinition of it doesn't like that. So let me do something. Let me go through all of these breaks. Oh, this is going to, yeah, I need to break it from the, okay. I'm glad I actually checked it. So I need to do this, and then I need to go through all of the cases. Like so, and I need to add this, and this should now work. Yeah, this should now work. And here, oh, it's, what? Oh, there was a break missing here. Okay. I'm glad this error actually happened. Yeah, I had a bunch of missing breaks. This will not work. Okay. And here I can have like a flag, say bool altered to false. And here, yeah, I can say, well, I can include standard boolean, I guess. So here, bool altered, this can be a while, and this can be while it did not alt. And here I can just set it to true, and it is going to terminate. Cool. Now, if I execute all of this, and it's still operation on PC may be undefined. What do you mean? What? What are you even talking about? Anyways, try to pop an empty data stack. Why is that? So doesn't this function, yeah, this function does increase. And now that I realized I need to start this from here, actually. It's very important, I cannot forget it. Try to pop a data, okay. So let me check the function. The program is this one. Well, I can do the following. I can come here and I can print the current instruction being executed, right? Why not? And say PC, so, and just check. Okay, so it's first executed the call, the literal. Why didn't it execute the call. What? There's something very strange. So let me debug this. So yeah, this is also debug. Let's say this is my memory. And here I can say memory pointer. This is actually 0. This is memory pointer. Right. This needs state for I. Yeah. If I do this, my memory is an 8, a 6, and so on. And an 8 is a call. So why does this... Oh, this is no, this is I'm so stupid. Okay, I need to actually print that. Okay, it's fine, it's fine. So this is doing a call. Okay, so this did a call, then it executed the literal, and then okay, so it didn't properly do stuff. Huh. So let me do something like this. So this is a lit, right? And here, if I do that, and oh yeah, because no, it's fine, it's fine. If I do this, and here, if I do something similar, so this is a call, and here I am calling this, and I'm saving. I can also store whatever I'm saving. I'm saving this, right? So that. Interesting. So it did a call. Ah, then this never printed. Can I do flush? Standard output. That is very strange. This operation on PC must be undefined. It's very weird. So if I do this like here, oh yeah, I cannot get that. Okay, I should be doing this. But nonetheless, it's so strange that okay. So this should be actually x1, and here I should be doing something like this. So I don't get all of those warnings. Oh, so the issue was the warning? What? That is very strange. Oh, anyways. So I do call 6 and I say 2. Sure. Then, so this is 0. This doesn't count. 1, 2. Well, yeah, I need to think about how I'm going to do this. This is not correct. Anyways, then I'm gonna do... So if I do that, then I do literal 2. That's good. Then I do call 2 and save 10, which is probably this one, or 0, 1, yeah, it doesn't matter, and save 10. Then I do literal 2, and then the add instruction is actually fucked up. So the add instruction is the one that's not working. Oh yeah, I see now. I see now. So this, if this is 0, yeah, and here I need to do that plus the offset, not the other way around. Makes total sense, yeah. And here is the same stuff, right? That minus 1 plus the offset, right? And to push, here I need to check the same thing, but here I need to push that plus the offset. And then for the return stack, exactly the same logic. So to push, I cannot push something that is bigger than memory size because the return stack is like at the very top. So here it's 0 again. And then I need to push it that plus the offset. So that was the mistake I did. So that, and here I do that, but I need to add offset. Okay, so this should, no, it's still fucked. So try to pop an empty data stack. Okay, so if I do pop, what is the value of my DSP at this very exact moment? So vm.dsp try to pop. Why did you try? Okay. And here, if I push it, okay. So it's 1, then why did it? Oh, okay, here. So we pushed, yeah, we pushed 1 literal. Fine, we called, we pushed another literal, it increased. Then it did a bunch of weird stuff. What the fuck is going on? So my add instruction, let's add printf for everything. So do this one, get that, and that's that. Okay, I just need, oh fuck, okay. Just need to do that and that, and do printf, and just start this string with that. So we have like a better idea of what the fuck is going on. So yeah, we pushed that, we pushed another one, and then we add it. Cool. Then, oh, this is not terminating, I see. So we called this, push the literal, which is that one. Then we called this, yeah, there. Then we pushed another literal, there. Then we added, and then we returned. And the return is fucked, I think. The return is fucked. Okay, there's something wrong with the return. Let me add some functions so I can understand this better. So I can also add for alts, and I can add for rets. But here in the return, I can do that there, and this is basically going to return into this program counter. Yeah, so it basically did this. Oh, the return is never happening. I see. So we are never returning. Do I have a bug in here? Yes, I do. Of course. Oh no, what am I doing? No, we do have the return instruction. So let's try to create a even simpler program. We just define two, we can say two, which just pushes two onto the stack, nothing else. And then a program that just calls two, and we quit, right? And then, well, we need to come here, add manually the alt instruction. If we execute this, okay, this worked. This worked. So why didn't the other one work? Huh. So let's say I define 2 and 3, or 2 plus or something, 2 plus, which is 2 plus that, and then I push 3 numbers onto the stack. I do 2 plus again, and then I can do something like a multiply, and that's it. Then I quit. Okay, if I do alt, so it's okay. So there's something very strange. It's something with the add instruction, I feel like. Am I popping from the correct DSP, DSP, DSP? So this is a push, and this is a pop. Right, let's try again. That. So it calls 6, which is this one. This should be a jump. It should not be a call. It should be a jump. But either way, we push literal 2, 3, 4. Then we call 2, which is this one, which pushes a literal 2. Exactly, and it adds, which pops these two and pushes. Cool. Then we should be returning, but we are not returning. Why are we not returning? What? Oh, well, yeah, I see what I did wrong. So I forgot something. I forgot that I need to increment my program counter. Fuck. So here, yeah. This one is fucked actually. Yeah. So this one, I could do this here so I can have exactly the same value, just to be sure. In this case, I can do postfix. I prefer postfix. And so this doesn't need anything special. Here I'm forced to do things this way. Here it's fine, here it's fine. Okay, but here I need to implement my program counter. So this was the bug. So the program was executing exclusively through the calls, right? So the program counter was only changing via the calls. Yeah, okay, so but now it also does stuff. So I do a call. Why did he? Oh, he tried to sub somehow. Okay, so let's go through it. I have the instruction literal, right? And if that's the case, I need to increment program counter, read the literal, and push it into there. Fine. Oh, I see. So I can only, fuck. Okay, I can only increment the program counter in these instructions. So I'll always need to add this here. I can add this here because when it is a call or a return, I cannot increment the program counter. All right, that also makes sense. So that's probably the issue. So That also needs a call cannot increment the program counter after doing this its own stuff. Otherwise, you're going to jump to incorrect place. The return can also not increment it. The alt doesn't need to increment it. So that was the issue. All right, so it's actually working now. Cool. And here, here I need to start from 0 up to there, and here I just need to use the offset. Yeah. Why do I? Yeah, it may be actually correct. So, do I want to have? Let me not have all of these printfs. I don't care about them for now. Let's do something like that. And then, oh yes, all of these pushes and stuff, I don't need them. So where, okay, it's here, and it's here. Okay, so this program basically does 224. So let's do something. Let's have like a example.pf or something, and here let's define the function 2 plus, which does 2 plus that. Then we can push 3, 4, and 5 onto the stack. We can add 2 to this, so this is going to be 5, 6, 7. So this is going to be 7. We can multiply, so 7 times 4, right? Which is 28, if I'm not mistaken. And then we can do 3, I don't know, 3 plus 28, for example, which should be 31. So this should output 31. And when we execute this, we can have something like example.sh, just to simplify things. Here, we can do that. We can echo whatever is inside example.pf into this. So we can pipe it. Then this is going to produce output file. Then we can just get this and compile that and execute that. And this should automatically do all of the stages. Example.sh, yeah. Fuck, example. Yeah, so I can, yeah, I should use cat instead. Okay, let me do cat. Okay, this is not what I wanted. Why are you prompting me with stuff? Oh yeah, I see. Fuck. Okay, let me just copy paste and have the example ready, so I can do it. And I still needed to append the alt instruction, but paste. Okay, and then I quit. Oh yeah, let me retry again. So if I bring back the example, so yeah, I can, if I cat example.pf, I'm going to get all of this shit. Okay, then I need to also quit. Let's say quit, like so. Then I need to run this. So this, what is this going to do? Yeah, this is the thing that it needs to do. It's fine. This is going to output the file, which is correct. It is a correct file. Then I need to this output file, I need to echo alt into the output file, right? So if I do this, it's going to, yeah, do this thing correctly. Here I can redirect this. I think it's, what was the redirect stuff? It was like this. I don't know. And then yeah, let's try that again. Okay, so it's working. So this script is going to execute all of the stages and then do all of the patching that is needed. But at the end of the day, like we can work with this directly. So we can just write our program in this file, and for now, and it's going to output like the final result, the final data stack. So let's, I don't know, so we have 3 for, let's do something like 2 times, which is that, for example. And here, if we do 2 times, so it's going to be 4. And then we can add 2 to 4, so it's going to be 6, right? And then we push 1, right? So it's going to be 6 and then 1. And if we swap, it's going to be 1 and then 6, right? Yeah, so let's see if this is correct. Yeah, it's correct. So 1 and 6. So it seems to be working more or less well. And with this app, like with this video, we more or less understood how this like VM should work internally, right? What are the needed components? So the alt stuff I still need to check. Like I still need to think about exactly what I want in this intermediate representation to have it like properly doing stuff. But yeah, I mean, it's more or less working. So if I wanted to actually do this in directly machine code, right, or in assembly, let's say, I would need a single register for the data stack, a single register for the return stack. I would need like the usual program counter, but I would use like the default program counter, right? Because each instruction would be its own thing. And I would need like a chunk of memory. I would just need a chunk of memory. And it would basically work. Yeah, it would basically work. So yeah, this was quite a useful video. So there are still a few things that I need to think about. So first, let me check if recursive functions work. So if I create a function like recursive, and this recursive function just appends one to the stack. Yeah, why not? And you go recursive. This should like alt. Well, it did. Oh yeah, I forgot. So this pushes one and then call recursive again. So this should like exhaust the data stack if everything is fine. Now let me bring back these things because it may be useful. Well, I forgot this points. Okay. If I do that, yeah. So it keeps pushing literals and then call, and then literal and then call, literal and call. But shouldn't this like exhaust the thing? Let me check again. So if I just print my DSP here, just for the fun of it, yeah, okay, so it's just slow. It is simply slow. Or not, is it? So it gets to 1026, and instead of like blowing up, oh, I see. So I must actually, yeah, that was actually a good test. So here I can define stack size, and this is a stack size here. Then this is going to be basically here, and that is going to be that plus that, right? And here I need to check it not against the offset, but against the stack size. Exactly, against the stack size. Yeah, this was correct. And that's, if I try, what am I doing? Yeah, if it's like this. So if RSP is greater or equal than stack size, it also blows up. So now this should blow. Yeah, it's okay. So this is like the Stack Overflow error from C, right? This is what we expected. So recursion is working. Recursion is actually working. The only thing that is not working from the previous episode are the macros, but I still need to think about that. So if I do like macro and I do this words 1 and then say 1 and then I do that and I call it macro, this is not going to work. Yeah, but it's expected. Yeah, undefined label in call. Oh, this is actually, yeah, it's completely fucked. It's completely fucked. But nonetheless, it's a nice exercise. Yeah, but we have at least recursion, which is a lot more important than macros. And it has an expected behavior. So 2 hours and 15 minutes. I think that's enough for this video. These first two videos were just like a trial, right? I was just doing very sloppy codes. I didn't really care because I just wanted to test the idea. There are still a few loose ends because I still need to define exactly what I want from the language. So do I want to support macros that I had in the previous episode and still have like machine code stuff? Do I want, I don't know, like, I think, yeah. How do I want to execute this? Like, do I want to have types? Do I want to have a bunch of other stuff? I need to think about all of that. And yeah, I need to think about all of that, basically. I think I'm going to think about that offline because I don't have a clear answer right now. Types would be cool, and I'm thinking about having dependent types for some reason. But I don't know what value that would have in a Forth-like language, to have a Forth-like language with types like from Agda or eGrid or something. eGrid programming language or Ingrid. Yeah, I think it's Ingrid. I don't know what value I would get, or Agda. I can search for Agda. Agda, yeah. These types are more powerful than Haskell types even. But I don't know. Because they allow you to prove, right? To prove stuff. So with dependent types on top of a forced like system, we would have a forced system capable of proving that mathematical theorems. Is that even useful, right? I don't know. But at least like some form of typing, static typing, I would most likely want to have, right? That's for sure. So yeah, maybe in the next video I'll keep working on like the idea itself and just trying a bunch of different things. Maybe I can move to assembly and just do the entire system in assembly without using any C, which is generally what people do, right? And yeah, I think that's it. So thank you for watching, and I'll see you in the next one.